So the man you see on the board here, his name is Artem Shek. He was a Ukrainian soldier and a journalist who writes about how for 5 days he was pinned down in a trench with no access to food, water, or for our specific use case, first aid. So his story is just one example that highlights a need that General Atomics has tasked us with filling. Hello everyone and welcome. Thank you for joining us on this cold December morning. We are MEDAID, consistent with Amarillo's background culture that stands for Multiple Environment Deployable Aerial Item Delivering. And this is our preliminary design review. So capstone is 2 semesters. This is the first semester. Next semester we'll be back here with our design review. So we're very excited over the next 40 minutes to share what we've been doing for this semester. And we broke it down into 8 sections over 40 minutes, and then we'll leave about 10 minutes for questions and answers. So how this is going to go, I'm going to introduce the team, and I'll provide a quick overview of the team structure. And then I'm going to hand it off to systems, and they're going to talk about what we've been tasked with by General Atomics, our sponsor. And then systems is going to hand it to our chief engineer, and he's going to talk about our approach to our solution. And then we'll talk about our solution. So the aircraft that we've built, and then as well as some of the highlights of performance and other things. And then we'll talk about some of the verification we've done and we'll plan to do next semester. And then we'll have time for questions. So getting an introduction. So my name is Jordan Richard. I am the program manager. On the other side here is Carson Curley, our chief engineer. We have Danielle McCormick, our systems lead. Alex Card, our systems engineer. Jackson Haggerty, our other systems engineer. We have Evan Highland, our structures lead. Sam Trukauer, our structures engineer. And Cameron Bound, our other structures engineer. Bear with me, there's 16 of us. So we have Zach Bauer, our manufacturing lead. Jacob Sander, our manufacturing engineer. We've got Max Welliver, our aerodynamic stability and control team lead. Isaac Weatherby, our stability controls engineer. Jackson Carlick, our aerodynamics engineer. Jeff Wang, our propulsion lead and our aero model lead. And Nick Barrick, our propulsion engineer. And then finally we have Cooper Guspold, our propulsion engineer and our aero model engineer. And then last thing I'm going to introduce is the team structure. So there's 5 teams on this team, or 5 sub-teams. So we have our aerodynamic stability control team, a systems team, a manufacturing team, a structures team, and a propulsion team. But note, this has been kind of fluid over the semester as the workload changes. Cool. And that's it for introduction. So I'm going to hand it over to systems, and they're going to talk about what General Atomics has tasked us with building.
Thank you, Jordan. For the next slide, I'm going to give a brief overview of some of our system requirements. We have a comprehensive list of system requirements totaling above 50 requirements, so we're not going to go in depth on that today. However, a few crucial requirements that have driven our design process. I want to start off, we have the objective of storing internally and deploying 2 medical canisters. You can reference the cylinder on the table. These are a length of 10 inches, a width of 4 inches, and these each weigh 5 pounds. They are not weighted to scale. The endurance threshold, so this is the minimum we need to achieve, is 3 hours. Our objective is 4. Our one-way range threshold is 150 nautical miles, objective of 200 nautical miles, and our altitude threshold is 10,000 feet measured from sea level. Our objective is 12,000 feet. We need to reach a dash speed of at least 100 knots. And finally, our stow requirement is from the leftmost edge of the aircraft to the rightmost edge, must not exceed 24 inches.
For our concept of operations, we have 2 methods of takeoff. One of them is an airborne, where we will launch off of another aircraft. The other is a traditional takeoff through a runway or ground strip. If we're taking the air drop method, we will have to deploy the wings after it has been dropped to avoid clashing with anything on the mothership. And from there, we will follow our pre-programmed waypoints to our drop points where we will make the drop. After we've made all of our drops, we will then switch to our landing position where it can be later retrieved. Now that we've seen the design process, the requirements, I'm going to hand it over to our chief engineer for our design process.
Thank you. Moving into our design process here, we started the semester with competitor research, where we identified 5 competitors with similar mission, range, or endurance requirements. From there, we created a baseline design based on this competitor space, using strategies like weighted averages based on payload fraction. From there, each of the team members brainstormed a configuration idea to superimpose this baseline design onto, focusing on high-risk areas such as payload deployment, wing packaging, and propulsion system. Not only what type of propulsion we'd use, but where we'd stick it. After that, we narrowed these 16 configurations into 3 top choices using a weighted average technology assessment matrix. However, we weren't too happy with any of these choices because they presented a lot of design risks. So we created a final configuration based on solutions to these perceived risks. This is the design that we've performed our detail work on that you'll learn more about over the course of this presentation. I'd like to present to you a couple of diagrams about how we size the aircraft. The first is a constraint diagram of wing loading on the x-axis and power to weight ratio on the y-axis. 2 constraint lines here are plotted, one for our top speed of 100 knots, the other for our maximum altitude of 12,000 feet. Any space above these constraint lines is a valid design space. To kind of analyze these constraint lines, I'd like to ask you to imagine a constant weight aircraft, so that as wing loading increases, the wing gets smaller. The top speed power requirement decreases as wing loading increases, because that smaller wing translates to less parasitic drag, while the maximum altitude power requirement increases because the smaller wing is less effective at offsetting the effects of low density at high altitudes. Our design point is plotted here at a weight of 50 pounds for our 10-foot squared wing area. That's a wing loading of 5 pounds per squared foot, and a power to weight ratio of right about 17 feet per second. These red lines here are a sensitivity analysis. The vertical span of the lines represents changes in drag from a 5% under prediction in drag based on our MATLAB aircraft sizing script, and a 10% underestimation of drag, or overestimation of drag. We believe that we're overestimating drag because of some simplifications we made, such as a circular fuselage that spans the whole length of the aircraft, which you'll see isn't quite right. The width, the horizontal span of these lines, represents different weights of our aircraft for our 10-foot squared wing area, from the perceived minimum weight of 45 pounds to the FAA regulatory maximum of 55 pounds. As you can see, a lot of this sensitivity analysis falls outside of our constraint lines, but MEDAID believes by increasing the power to weight ratio by about 2 feet per second, which is very doable with our engine selection, we'll be able to fall completely within the constraint lines, the design space. Next is a range and endurance versus velocity plot. Velocity on the x-axis, range and endurance plotted on the y-axis. MEDAID's mission of reaching a down soldier necessitates as high a cruise speed as possible. And here we can see that a cruise velocity of 60 knots will meet both endurance and range objective requirements simultaneously. However, best range and endurance speed falls in the 35 to 45 knot regime, while the dash speed significantly reduces range and endurance. This shows that a mission designer has a lot of flexibility in trading speed for range or endurance. Now that we've looked at what the aircraft needs to do, I'd like to pass it off to the structures IPT to talk about how we're going to do it.
All right, this is our preliminary design solution that we've called the XM24 Kestrel. Moving forward to aft, I'd like to point out some fuselage features. We have our engine here. It is mostly encased in the fuselage for aerodynamic benefits. However, we have left our carburetor and our engine cylinders sticking out for cooling and airflow purposes. Moving aft, we have our fuselage strakes here. This is a sort of complex fuselage shape that allows us to cover our wing folding hinges. While we're talking about our wing folding, we'll look at our flaps here. You'll notice that they cover our entire trailing edge all the way up to our aileron. In order to keep sufficient wing root for our wing area, we needed to fold these flaps down next to each other. They'll sit flush to each other like that. That allows us to bring our wings side by side here. Our ailerons do have a little bit of clash here right at that point. However, this can be dealt with a very slight deflection upward and downward from each one. We also have our upper surface of this fuselage is a regular, constant radius curve, which will allow us to interface smoothly with the sway braces on the MA4 ejection rack, which we'll be mounting to with these standard 14-inch lugs here on the top surface. Moving further aft, we transition to a boom tail. This allows us to reduce both drag and weight in the aft section of our aircraft. We have our vertical stabilizer. Our rudder is only on the top half. However, we have added a ventral fin just to increase our vertical stabilizer area. And then finally, of course, we have our horizontal stabilizer. Now that we've covered our major external features, we'll go onto that all-important feature of the wing folding.
So taking a look at our wing folding mechanism, it starts in the stowed position. In the stowed position, there are clamps on the aft side, on the bottom of the fuselage that will hold it in place. And there will be bands that will be wrapped around our bearings that will be in tension in the stowed position. Once these clamps are released, the wings will swing out. Unlike the wings, the flaps are just held down by contact with each other. So as the wings deploy, the flaps will return to a clean configuration. Once the wings are fully deployed, the latches on the innermost rib will lock into the fuselage and the wing deployment will be complete. So moving on from that, we'll take a look at some of our major dimensions. So in the fully deployed position, we'll have a wingspan of just under 11.5 feet, a nose to tail length of 7.5 feet, and a tail height of just under a foot. And the stowed configuration, our wings will fit within the 2 feet constraint, and our tail width will be the maximum of 2 feet. So that will allow us to meet our design requirements. Moving on from our external features and some major design choices, we'll take a look at some of our internal features.
So this cutaway shows most of our primary internal components. As you can see, all of our components were positioned relative to this reference line with the goal of getting our CG position as close to center between the lugs as possible. Our CG is currently at 24.8 inches, which is less than 1/4 inch farther forward than that goal. So moving forward to aft, we have our standard tractor propulsion system with an engine mounted to a bulkhead in the nose. Moving aft, we then have our avionics suite. This includes our data link, receiver, starter battery, things like that. And then we've got our first fuel tank. This fuel tank is purely reserve. It's not included in any of our mass or CG calculations currently, but if we decide to add more fuel later on, that's where it will go. Then we've got our first bulkhead for the lug mounting, and then we've got our 2 primary tanks, our payload canisters, and our wing deployment hinges. It's a little difficult to see in this cutaway, but we have two primary tanks, one on each side of the canisters. And the canisters are stacked vertically on top of each other in center so that once the wings are swept outwards, they fall between the wings for deployment. You'll also notice that they are mostly centered on our CG position so that when we drop our canisters or when we burn our fuel, our CG barely changes. Continuing aft, we have our second lug bulkhead, and then our wing release clamps, and then our final 2 bulkheads that attach our tail to the fuselage. So now that you've seen our current design, I'm going to pass it over to propulsions and aerodynamics to talk about how it performs.
Thank you. First, a few requirements that drove our propulsion choice. The ground roll distance at testing elevation must be less than 200 feet. The thrust produced at dash speed for sea level conditions must be greater than or equal to 8.5 pounds. And the thrust produced for dash speed at our objective service ceiling must be greater than or equal to 6.5 pounds. And then it's best for all parts to be sourced commercially available off the shelf. We then analyzed turbojet, turboprop, piston, and electric engines that met those requirements. Due to the fuel efficiency at our cruise speed and elevation, it was determined that the piston engine was the best choice. And then it will need an electronic fuel injection conversion for operational safety and autonomous compatibility. The piston engine fits within our budget requirement given by the customer. However, it does not fit within the team's budget for a demonstrator. The solution to that is to use an electric motor, as it will be able to prove all system requirements excluding range and endurance, but it'll still be able to give us data, and we'll be able to extrapolate the final product's range and endurance.
Now, with our power plant discussed, let's look at our propeller. For the propeller, we chose a Zinger wood laminated propeller. This propeller has a 22-inch diameter and a 32-inch pitch. This propeller is expected to produce around 30 pounds of thrust at static with the power plant that we've chosen. And all of the factors of the propeller together yield a pitch speed of roughly 158 knots at the 6,000 RPM that we expect the loaded power plant to produce at full throttle. Next slide. And now let's look at a sample mission for this aircraft. First off is the takeoff. Takeoff is defined as the section of the mission between when the throttle is first advanced to when the wheels come off the ground. I estimate that will take around 30 seconds. During that time, we will be going full throttle, and full throttle for the engine we have chosen will burn about 9.1 pounds of fuel per hour. Next up is climb. Climb is a climb at our maximum climb rate to 5,000 feet above ground. I estimate this will take about 3 minutes, and again, we will be at full throttle for this entire section of the mission. Next up is cruise. Once we have reached our cruise altitude, we will back off on the throttle to our cruise throttle, which will burn about 1.75 pounds per hour. For this mission, I estimated that cruise would take about 3 hours. Next section is dash. In case we are approaching, say, a front line or some other dangerous situation, we may need to descend, and we will need to speed up to our maximum speed. During this time, we will be at full throttle again, 9.1 pounds per hour, and I've assumed 10 minutes for this simple mission. Next up is descent. Once we have done our cruise, done our dash, dropped our payloads, we are going to then turn around, approach the landing zone, and descend from whatever altitude we were at the end of our mission to a proper pattern approach. This, I estimated, would take 3 minutes. During this phase, we will be roughly idling the engine and burning very little fuel. Finally is landing. Landing is the point where we actually finally take the aircraft from the approach to on the ground. I estimated this would take 1 minute, and again, very low throttle setting for this, about half a pound per hour. Altogether, this mission would take about 3 hours, 17 minutes, and burn a total fuel of 7.3 pounds. Obviously, there is flexibility in this depending on how full we want to fill the tanks and which sections we want to do of the mission, when and where and how. Now that I've talked a little bit about the propulsion system, I'd like to hand it off to the aero team to discuss some of the aerodynamic parameters of the craft. Thank you, Nick.
So now that we've discussed our propulsion, let's look at some of our wing designs. First off, on the left side of our on our table, you can see our characteristics of our wing. We have a wing reference area of about 10 feet, a taper ratio of about 0.7, an aspect ratio of about 10, and a leading edge sweep of about 2 degrees. You'll notice the 50-degree tip. If you look on the bottom right-hand side of the slide, you'll see the wing tips. That is the leading edge sweep for the wing tips. Next is the key parameters at our cruise conditions. You'll see that we have a CL of about 0.5. This comes from an angle of attack of close to 1 degree. We have a parasitic drag of about 0.03, a L over D of about 11, and a lift curve slope of about 0.1. So as our chief engineer talked about earlier, we have a code to estimate our drag. This is for the entire aircraft, not just our wing, not just our fuselage, the entire thing. And as you can see on the left-hand side, we separate the entire aircraft into different components. And then on the top of the table, you can see that we separate our drag coefficient into 3 different components as well. The code solves for each component of drag individually for each component of the aircraft. And then on the left-hand side, you can see us total this all up, and it comes out to about 430 counts of drag. And in the end, for our aircraft specifically, this comes out to about 3.9 pounds of drag. Next, let's talk about our stability aspects of this plane.
So our tail configuration was mainly developed through a MATLAB code, which would analyze many different tail configurations for different selected wings, and then optimize based on aspect ratio to reduce drag. You can see the dimensions here in this table and an image as well. Some key points I'd like to make about the tail are the highly tapered portions, which is vertical stabilizer, and also our airfoil choices for the tail. The vertical stabilizer will have a NACA 0008, which should be thick enough to contain all structural components like spars, and our horizontal stabilizer would be an inverted Celix 775, which is actually the same airfoil used on the main wing. Our control surfaces, as you can see here, will be responsible for trimming different produced conditions or any performing maneuvers necessary for missions. As you can see here, we have some static stability criteria. We have CM versus alpha, which represents our pitch performance, and as you can see, it is negatively sloped, meaning that as we pitch up, we'll be getting force or source back to our neutral condition that we've trimmed. But then we have our CN versus beta, which is our yaw stability. As you can see, it has a positive slope, meaning we'll be yawing into side slopes, which is in line with stable aircraft. And then for our CL versus beta, which is our roll stability, we have, again, a negative slope, meaning similar to pitch, we'll be returning to our neutral roll state. A point I'd like to make here about our roll stability is we have some irregular points. This is likely due to the aerodynamics of our fuselage and tail as they clash with different beta values.
All right, so next we have our lift to drag plot here. So on the y-axis we have CL divided by CD, and then on the x-axis we have velocity in knots. So the maximum point on this plot is the L over D max of the aircraft, and it occurs at 50 knots and gives us an L over D of 11.5. We're operating 10 knots faster at 60 knots here, and an L over D of 11.16. So we're sacrificing a little bit of L over D for increased speed. As Carson already showed us, we meet both the range and endurance requirements, but we can get to the down soldier a little bit quicker than if we were flying at 50 knots. And then next we have our CG excursion diagram. So on the y-axis we have gross weight in pounds, and then static margin on the x-axis in percent. So you will notice it's a straight line, and this is actually a best case scenario for us. So this is once again because our fuel tanks and then the payload system and the payloads itself are over the CG position of the aircraft. So as we burn through fuel and we drop the payload, our CG doesn't change. And so we start out here at 50 pounds, which is the max gross weight, and then burning through everything and dropping both payloads, we go down to an empty weight of 32.5 pounds. You will notice our static margin is a little bit on the high side, sitting here at around 23.6% static margin. We've built in a little bit of margin here in case during the manufacturing process the tail becomes a bit heavier, reduces our static margin. We'll still have a stable and flyable airplane. So now that we've talked about all of our aerodynamics data, we'll now jump into design verification and how we've done that with the aero model.
Thank you, Max. Next, we're going to talk about design verification. As you can see on the table, we have our aero model built. This is a fully 3D printed 60% scaled down version of our full scale design. This choice was made for reduced cost and ease of manufacturing. Although this model does not represent our full scale perfectly, this geometry represents our model used for flashing CFD perfectly, and it also represents the model we use for our MATLAB simulations. By conducting flight tests of the aero model, we were able to validate some of the simulations and calculations we did during the design process. For example, the MATLAB code drag estimation, especially lift to drag performance, and this, the data we gathered from this aero model was able to validate the flight stream CFD analysis, and therefore validating the use of this software for future analysis. In addition, conducting flight tests can validate the stability of the aircraft, and based on the feedback of the pilot, we have an expectation for how this airplane handles in the air. After that, some recommendations were made to the team. One of the key points is to enlarge the vertical stabilizer. As you can see, this vertical stabilizer is one of our previous designs. It is rather small and does not give the airplane enough roll stability. Therefore, this recommendation was recommended to the team. In addition, installing a gyro stabilization system can help the airplane to fly stable and make it easier for the pilot to control. Next, I'm going to pass to our manufacturing team to talk about subsystem prototype.
As MEDAID enters the production phase next semester, subsystem prototyping will assist the team in developing a final flight test article. After determining high-risk systems, the team will be able to perform iterative testing to refine the design. By prototyping systems like our wing and payload deployment, we can ensure their successful operation. By producing different components of the aircraft a few different ways, the team will be able to make final material selections.
Now we will dive into our wing deployment prototype. The prototype will be able to go from the stowed position to the deployed position. Once the prototype is able to do this with ease, we will test and verify all components of the prototype. After, we will modify any necessary materials or invalid structures on the prototype. And during the design phase of next semester, we plan to model our fuselage and wing structure, along with having a servo to actuate our deployment, along with a latch to catch our wings as they deploy. Now I will hand it off to systems to go over the method for which we came up with our risks.
Okay, thank you so much. So going into our risk analysis, this was conducted using SAE standards, specifically ARP 4761A. This right here is a risk matrix. Due to time constraints, we're not going to go dive into all of our risks, but we have 27 identified in the categories of operational and technological. This matrix here, the x-axis, is the impact that a risk would have on our aircraft, going from insignificant, so low change in the effects of the aircraft, up to catastrophic, which is either loss of life or loss of aircraft. On the y-axis is the likelihood of a risk occurring. The color coding here stands for the priority of the risk, green being low priority, yellow being medium priority, and red being high priority. Any risks in the yellow or red categories require mitigations and specific testing validations to assure that maybe the likelihood is separate or the impact is less than we expected it would be. The green we accepted as a risk.
Thank you. So looking at our risk analysis and going based off of our risk matrix, some of the risks that we've identified are listed here. We have two high risks for wing deployment. We have one high risk and two medium risks for the propulsion system. We have two medium risks for the payload deployment, and we have two medium risks for the fuselage composite. I will now hand this off to our chief engineer to talk about test bedding.
So based on the work of the systems and the manufacturing IPTs, MEDAID has identified 3 subsystems and 2 models that we'd like to build over the next semester. The first of the subsystems is the wing deployment mechanism, which will be a full-scale model to test both the stowed and deployed lockup and performance characteristics of the wing. This will be using the manufacturing methods outlined by the manufacturing team, and a full-scale successful article will be used on the final flight test article, reducing our workload later on in the semester. Another system that we'd like to prototype is the payload deployment subsystem. It's a high-risk system, but again, this will be a full-scale model to test the reliability of deployment at different aircraft attitudes. Here, we'll again use that on the flight test article, pending a successful test. We'd also like to acquire an equivalent electrical propulsion system. This is a propulsion system that produces the same power output as our identified piston engine and can be used to verify manufacturer specifications, or at least find the fudge factor that they build in. This will be used on our final model, as mentioned, to validate all requirements that can be validated with our flight test article, with the exception of range and endurance due to the low energy density of electrical propulsion systems. The models we'd like to build are a wind tunnel model and another aero model. The wind tunnel model will be used to test the performance in both the folded and unfolded configurations, particularly the stability of those configurations. We're pretty confident in our stability analysis for the fully deployed configuration, but there are a lot of unknowns in the folded configuration, especially as it relates to the deployment dynamics. We hope this experimental data will allow us to kind of nail some of that deployment stuff down. We do anticipate that matching Reynolds numbers will be impossible with the facilities at Embry-Riddle. However, Dr. Traub has given us some research and some methods to extrapolate drag values to different Reynolds number conditions. Finally, we'd like to build another one of these. This one unfortunately separated the back half of the fuselage, but this new aero model will still be fixed wing, but we'll have a more true fuselage design to our flight test article and allow us to rapidly iterate and identify design changes that need to be made, Although we do think that collecting data will be challenging, especially as it scales with the different mass moments of inertia from a 3D printed model to a composite and foam layup model. So that's what we plan on doing next semester. I'll give it back to our PM to talk about how we're going to get there.
Yeah, so before we do that, I'd just like to summarize what we talked to you about today. So you've met the team, and we've tried to introduce the project. What our sponsor, General Atomics, has been tasked us to do. It's build an airplane that delivers medical aid canisters to downed soldiers. So we talked about our approach to a solution, and then we talked about our solution and some highlights. And then we talked about how systems identified some risks, how our chief engineer identified tests we want to do next semester to mitigate those risks, and so it's my job to fit that into the schedule. And so here are our working plans for next semester. You see it's broken down into 3 phases, phase 1, phase 2, and phase 3. So phase 1 of next semester will be 4 weeks, where we'll take those subsystem prototypes and we'll define their use, what we're testing it for, we'll build them, and then we'll do a formal test readiness review before we test and generate a test report. We'll then take the results of those tests from the test report and we'll do a design cycle. So we'll have 3 weeks in phase 2 to do a design cycle to make any changes we need before we lock in our design with our technical data package and our critical design review. And then we'll have the last phase of next semester, 8 weeks. We're going to build our final design. We'll do a formal flight readiness review. We'll test it and then validate our requirements and generate a final report. And then we'll be back here in May. So that's it. That's all I have for you. We put in a lot of work on this project. We're very proud of it. We put in 3,700 hours this semester, and we expect to do the same next semester. We'd like to incorporate any feedback we get from this presentation into our plans for next semester. So with that, are there any questions? Yes.
All right, so I have a couple of things.
Sure.
First of all, I want to say I wish I had this big of a team when I
Yeah.
Sorry, Dr. Northling, but yeah, I wish I had this big of a team. So first, can you go to page 19? We had your diagram.
19.
So it would have been helpful if you guys had made another one of these slides where you actually show your dimension, especially your CG location,
Absolutely.
of how far it is from the reference line.
Yeah.
And you guys mentioned that you guys didn't account for fuel burn into your CG calculations from full to empty weight.
Yeah, so we did. It's kind of hard to see in this image, but on the back side of those blue canisters, and then on the other side, there's our side fuel tanks, and those are our primary fuel tanks. So we're going to burn from those. The forward fuel tank that you see there is not used currently. We've built that in this margin just in case we need more fuel. Then we'll have to kind of recheck our CG location as we burn through fuel. But right now, since the centroid of those fuel tanks are over the CG position of the aircraft, we can burn through without any CG change.
And then can you go back to the slide where you had your CG chart?
Yeah.
I think you mentioned this seems very optimistic.
Yeah.
So because you have fuel, and with that payload, and are you guys expected to, when you guys are doing flight testing, to drop the payload?
We'd like to.
So, given that the payload is right at CG, and since you probably won't have a rapid CG change, that's good. But then if you incorporate that forward fuel tank, that's going to account for your CG location. So that's something to consider, because depending on which way your CG shifts, that might change your aerodynamic characteristics. Speaking of which, and if you guys do that, consider your longitudinal stability. Do you guys statically stable longitudinally?
Yes. Okay, that's a good point.
So just keep that in mind. If you guys are going to incorporate that forward fuel tank, your CG might shift forward a little bit. One of the big concerns is if your CG ever shifts aft, you might end up having a higher pitching moment.
Thank you.
You go to page slide 30.
This is like
This is 30. Okay, I can't see the page. And you guys already conducted a little bit of flight testing already?
Yeah, so we built a 60% scale aero model, and Jeff can talk more about it.
Yes, what would you like to know about the flight test?
No, good on you for doing flight testing. It's only the first semester. And I like that you guys got recommended to increase to make the vertical tail bigger, because by just looking at the model, like, given the size of that, and your rudders are probably blanked out by the fuselage.
Yeah.
So that's good. And then can you go to page slide 37 for your risk assessment matrix? So you guys have identified these risks. I would have liked to see, just for my brain coming from flight testing, is you put it on that matrix of where it's considered.
We did. So we only had 40 minutes to present, so we had to cut a bunch of material, but we have additional slides to share with you. So where is it? Somewhere. There's a lot of slides. Okay, there it is.
Yeah, this is our operational risk matrix. We have 13 identified here. Then we also have our technological risk matrix, which is the next slide, which we have 14 identified. We also have our risk matrices post our mitigation, seeing how likelihood or impact will change, which is also the next two slides. A lot of these stay in the yellow as well, which is why these are recommended to go into next semester as subsystem prototyping.
I would have liked to see, at the very least, you guys talk about your risk matrix after your mitigations, you implement mitigations, because a big part of flight testing is the safety aspect. And you always have to consider what is what you're testing, what is the hazard, such as loss of aircraft. What can cause that hazard? How to mitigate that risk? How do you and then the effect of it. So I would have liked to see just a brief mention of this, that you guys actually did consider it. So that's good. And then just as you're starting to think about doing more flight testing, especially when you start building your full scale model, also keep that in mind, because safety is always a huge thing. Because coming from flight testing for the Air Force is always the biggest risk is is the system under test, and then also the pilot. So good that you guys did consider it. And then can you go to your slide 38?
Bear with me.
Yeah. So do you guys have a fully developed flight test plan yet, or no?
No, that'll be work for next semester.
Okay. And then can you go to the schedule slide?
Yeah.
So I do like that you guys have thought about this through going from making your flight test plan, then to testing, then making a report for it. So that's good. And then a lot of things to consider with flight testing is that you have to do a build-up approach. You can't just first thing we do as we flight test. All right, we're gonna go to the max airspeed of this thing. No, you can't do that. You have to start small. Well, one, can you take off, land, and can you just fly around in the heart of the envelope, the aircraft's happy space. From there, once you get the results and see if all right, it's good, then you can start going faster, going higher, and stuff like that. So that's something to consider when you're making that flight test plan. And then in regards to the schedule, having experienced this 3 years ago in CAPSA, and also now with my job, is that schedules aren't fixed. There's stuff that can happen that may be out of your control. So consider that if there's something that's that's delayed, and that could have cascading effects on getting to the most important part, which is flight testing. Because the flight testing time is very when I did this 3 years ago, we had 1 week to flight test before the CAPSA presentation, and we crashed. So have plans in place of if something gets delayed, what can you do?
Yeah, absolutely.
Let's take time for some other questions.
Yeah, I'm done.
Yeah, nice job, you guys. Super polished presentation. I really like the work you did. Especially the intro, you kind of warmed everybody up and got us into it, so even on this cold December day. But I really like that. Question I had, though, was on your side fuselage tanks, or fuel tanks. Let's go on the inboard profile view. I think that these tanks straddle the CG, correct? Your side fuel tanks? Okay.
Correct.
Think about the case where you're at the end of the mission, you burned off half your fuel, maybe 3/4 of it, pitch the nose down, the fuel in those tanks is no longer going to be evenly distributed. It's going to go to the front, right? You want to make sure that your elevator control has enough authority to bring the nose up. Otherwise, you're just going to plow into the ground, right? So size your elevator accordingly, and if you can take steps to mitigate that fuel slosh, that will also help your pitch stability in flight. Otherwise, you're going to have this porpoising effect going on as you fly. So it's not something that's evident when you actually lay it out in a static view like this, but it will get you later on. So, but otherwise, really good job. Nice work, guys.
Thank you. Thank you very much.
Real quick question, sorry, on your envelope of your mission envelope. I don't remember what it's like. Yeah. So you have a cruise phase for 3 hours, then you drop the payload. And so is there a cruise to go back, or what is your intent between dropping and landing?
Right, so the idea with this aircraft, generally speaking, is that it is essentially single use. It does not return to the airfield it started out from. It will land at some designated spot somewhere else. So once the payload is dropped, it will just go to that landing zone.
Okay. Yeah, I think it would have been nice to hear that at the beginning, because I was looking at it, like, how do you get the fuel to come back to your starting point? So otherwise, very good job.
I have two quick questions. One on your cruise conditions. Are you envisioning maximizing range during cruise?
So we are operating a little bit past the maximum range point, so 10 knots faster. We're still able to meet the range requirement for the project, but we're also able to get a little bit faster. If we wanted to operate at the max range, then we could fly at that slower speed at 50 knots in cruise.
So why are you flying faster than maximum range?
So that is mainly driven by the mission of the aircraft, and that we're trying to deliver medical supplies to somebody in need as fast as possible. So if we can fly, as close to the edge of that envelope as possible, then that would be the best way to go about it.
Okay. Then another quick question on operations. So how are you deploying your payload? I mean, I'm looking at this and I'm thinking, the simplest way would be to fly the whole thing upside down and just drop the payload, right?
Yes, so bear with me, we have a back slide for that somewhere. Right there. So this is what we've developed so far, and it's subject to change, but Carson can explain a little bit more how it works.
Yep, this is a single servo actuated payload deployment rack. There's a hole right in that vertical brace where a servo would actuate it. And so the resting condition is here. The payload sits on top of these two racks here, one on top of the other. To drop the bottom payload, we actuate the servo about that axis, tilts the bottom lifter out, the top one in, brings that crossbar in, that retains the top payload while dropping the bottom payload. Then we go in reverse to drop the payload from the top to the bottom rack, and then we go back to the resting configuration so that the second payload is now ready to be deployed using the same sequence here.
So it's dropping through the bottom?
Yes.
You don't have a lot of space there because of your folding mechanism for your wings.
The folding mechanism of the wings rests outboard of the payload doors, so when the wings are folded, we've been unable to drop payload, but as soon as those wings fold out, there's room for the payload doors to open.
So why not fly upside down? I mean, there's no good reason not to, right?
It's more of a design challenge that way.
See the hard plates on top.
Yeah.
Okay.
Other questions?
I saw you have I saw you have CG calculations, but what about for when the wings are stowed? Like, how much does it move with that, and any static margin? Okay.
Yeah. So we have backup slides in this fairly slide. asking about.
So that second red line, farther aft one, that's our CG position with the wings swept backwards instead of configuration. So it's behind our neutral point.
Yeah, it is something we're concerned about. So we'll try to do some testing, but unless General Atomics lets us have our aircraft off of theirs. Nope. Alright, Dr. Sev, you have a question?
Yeah, I was curious. So I saw that you had some MATLAB code and evidently some other code. I don't recall the exact name. I was curious, how do you think your design flow would have changed and your design approach would have changed if you hadn't had any access to code? Just maybe, you probably presumably started with pencil and paper and then went to the code. So if you had just the pencil and paper and had to go right to some application, what would it change, do you think?
Yeah, so our approach to the solution was first we looked at all the competitors that have a similar mission profile, and then we kind of developed a baseline design where it's like, okay, it kind of has to be about this big and have this mass fraction. And so we developed a MATLAB code that iterates, so we can rapidly iterate different configurations, and it'll tell us sizes of control surfaces and stuff like that. Carson's done a lot of work on it, so we can talk more about it.
Yeah, but I think your question was more about what we would do if we didn't have it, right?
Well, yeah, like maybe like say 50 years ago.
Sure.
Yeah. And so, for instance, did it allow you to accelerate your design process by a month,
Absolutely.
2 months, or something like
Yep,
that?
it was really easy to just change one parameter, tweak one parameter, see how it changed, create graphs based on that MATLAB code that kind of allowed us to follow a line. We're really grateful to have that tool available to us. Maybe we would have done the same thing 50 years ago, just with a bunch of 16 of us and pencil and paper. Hey Cooper, you changed the wing area by a foot squared. I'll change the span. But having that code really did accelerate the design process for us.
I will say it definitely had a huge effect when we were trying to close down on our design choices earlier in the design phase. Mm-hmm. And especially when we came to those final three and we're just like, there are so many problems that we could have with these three, so let's take what's good about these three and just put them into one. And so having that code very much so helped that process.
And am I correct in understanding that this flew?
This did fly.
It flew. So basically from pencil and paper to a little bit of code, and then you were able to fabricate this and then took right off. Great. Oh, that's amazing. Mm-hmm. Wow.
Okay. We did some backup analysis using flight stream CFD. So I make sure this thing can fly compared with our MATLAB result, and then flew.
Yeah. So you got two pieces of code we're using.
Yes.
Congratulations.
Thank you. Other questions? Really looking for your feedback. Yeah, Dr. Goffman?
A question on your drop, your payload. How do you know that you're dropping it in the right spot? How does that happen? You have onboard cameras? Is it remotely piloted? What is that process of payload delivery?
It's a good question. I can speak to that.
Sure. The RFP calls for a GPS guided drone, so we anticipate that we use a waypoint to drop. Once we hit this GPS waypoint, we would actuate a servo that drops the payload. There's of course a little bit more back-end work on that as far as that sequence of events goes. We don't intend to have an onboard camera to I guess verify that we dropped the payload in the right place. I guess we got to trust our mission planner there.
That is something we could incorporate. Yeah, sure.
So we have a system requirement that our payload must land within a 20-foot radius of the intended drop zone. This is something we plan to verify during our full-scale flight model, and making sure we have that sequence of drop fully documented out. So when we do send this over, and ideally in the field, the real one, as long as it follows this set of processes and these conditions, it will be able to hit target.
I have one more question.
Sure.
Do you have any idea on what the
size of the market is for this thing? Or where it might be deployed initially, like some of the early adopters, like Coast Guard or?
We have not really done any market analysis. We're all aerospace engineers, so we're just trusting General Atomics that they've done the market analysis. We're going to do what they say. So.
That's a good answer.
Yeah, Dr. Bennett.
How much, so in the event that this is unable to be recovered, how much is it going to cost? Like, what's the unit price of this?
Sure. Who wants to talk about that?
I can cover unit price. So we're looking at about $1,500 in terms of materials and onboard components. So crashing would be kind of devastating, but we do have room overhead with our budget to make a couple models.
The final model.
So the final model, I believe we're looking at about $14,000 if you were.
And the RFP?
And including labor for the first unit, we're looking at about $33,000.
So 50K unit cost over 100 units is the RFP target.
Yeah, so General Atomics has asked us that if we build 100 units, each unit's going to cost $50,000. Any other questions? We really want your feedback for next semester. Yes.
So you guys said that you're gonna have 2 payloads, right?
We have 2 canisters on, yeah.
Does your system, is it able to drop them both at once?
So,
no. The short answer is no.
The short answer is no.
Okay.
Yeah, they're stacked one on top of each other, so you'd have to drop the bottom one first, and then you could drop the top one.
Certainly in rapid succession, but not instantly 2 at the same time.
Okay.
As a follow-up to that question, would both of those canisters be intended for the same target, or would you be planning to hit 2 different targets with those canisters?
Either or. So we can have
either one?
Yeah.
Okay.
To follow up, if they are intended for the same target, don't forget to factor in like turning around into your fuel stuff.
Yeah. Yeah, more analysis to do for sure next semester with that.
Will the canisters always contain the same stuff? Like, are they always going to be the same?
Don't worry about it.
We aren't paid to know what's inside the canister.
So we asked General Atomics questions about that. Does this need to have some sort of like external power supply or anything? And they said, don't worry about it.
Just in terms of like the error model, if it's going to be always a consistent rate.
Yeah, it should be about 5 minutes. Evenly distributed our side. Other questions?
Well, I'll ask one more question on slide 28.
28.
Your C and beta plot has this really interesting step right around the neutral point or around the 0 side slip. Do you think that that's just real or what is that?
Which point are you talking about?
The central plot right at 0 degree side slip, there's like this flattens out, so it's basically you become marginally stable right around 0 side slip, whereas when you're further away you're stable again. So is that just artifact of calculations? Do you think that's
it's
real?
It's an artifact of the X-Flyer software.
Okay.
Also, I use MATLAB a lot, and it connects points sometimes in strange ways.
Okay.
But I believe we are stable in the.
Just something to check if you do wind tunnel testing. Just go really small increments in side slip right around -2 to 2, just to make sure that there is no weird thing going on, that you're not getting any interaction from your fuselage and your vertical tail, because that's definitely possible.
Right.
I have a bunch, but I got you guys thrown out.
Yeah. Got 4 more minutes if anyone has questions.
I have one more, I guess.
Sure.
Do you know what, maybe I kind of already asked this, but do you know what people are already doing in instances like this? I mean, for instance, let's suppose you wanted to do a helicopter and you've got a 3-hour mission time. How much does it cost to run a helicopter for 3 hours? That kind of comparison. Is this eventually going to probably must cost less than running a helicopter, is that?
Yeah, certainly. So we haven't really done the analysis on helicopters versus fixed wing. Carson, you can check it here.
Yeah, so Cooper, you freezing your hand.
Yeah, based on some of the competitors that we looked at, most of them were surveillance, and anything that had payload delivery had a pretty low range, typically for packages or for anything like that. This one, we have availability for both ground and air deployment, which means that it's tailored more to less accessible areas. So disaster relief, search and rescue can be used for a lot of different things.
And if I could add, there is, for our specific mission that GA gave us, there is a certain element of risk to sending either a manned aircraft or a large unmanned aircraft. They're potentially going towards a combat zone, and large aircraft are easier to see.
Oh, I see. Yeah, the military side of the military nationally makes a lot of sense.
Online question from Ziggy. If a single-use UAV, why not have it self-destruct after canister deployment to avoid enemy reverse engineering?
That's a good question.
Ideally, we would like to be able to recover this. So, for example, if we secure the zone, we might be able to send a truck out, pick up the aircraft, bring it back home. So, and also causing it to deploy or self-destruct after deploying the payload. We're ideally deploying the payload at a spot where we know the soldier we're trying to help is, and having it self-destruct near there would be highly dangerous to that person.
It's also weight is a big issue, so we're trying to keep as much weight off the airplane as possible. Well, that pretty much concludes our presentation. Thank you for coming.